So we're going to do some proofs with the isosceles triangle theorem and with the converse of the isosceles triangle theorem. So this first one, we're going to start with our givens. BD is congruent to BE. And let's mark that on our diagram. BE and BE and BD are congruent. We're also told that the measure angle 4 equals 50 degrees. So, what are we trying to prove here? We're trying to prove that the measure of angle 2 is 80 degrees. Based on this first given, and keeping in mind the unit that we're in, what conclusion can we make from that given that BD is congruent to BE? What conclusion can we make? Yeah. Good. Angle 4 is congruent to angle 5. Okay, so good. Angle 4 is congruent to angle 5. So we can mark that in our diagram too. How do you think we're going to involve angle 2? Because angle 2 is what we're trying to prove something about. How can we relate what we know to angle 2? Yeah. Hello. Yeah, triangle sum theorem. What would the triangle sum theorem say? Very good. Okay, so triangle sum theorem is always this general statement, right? You're naming the angles. You're not putting any degree measures in there except for the 180, right? You're just saying that the three angles of a triangle add up to 180 degrees. That's the triangle sum theorem. There were some creative things going on with the test with that for some people. So make sure you understand that that general statement is the triangle sum theorem, okay? All right, now what? What could we do to get the measure of angle 2? Yeah. Okay, so you're saying since the measure angle 4 is 50, and we know 4 and 5 are the same, yeah, so first we have to say the measure of angle 4 equals the measure of angle 5 by definition of congruent. Oops, I forgot to put the reason for... What's our reason for this one? BD is congruent to BE, so the sides are congruent, therefore the angles across from them are congruent. What is the reason? This is actually the theorem itself. Isosceles triangle theorem. So think about it this way. What is the definition of an isosceles triangle say? Like if you looked up isosceles triangle, would it say that there's two sides congruent, or would it say that there's two angles congruent? Sides. Isosceles is typically classification of triangles by sides. We usually put it with equilateral and scalene, right? It's either scalene, equilateral, isosceles. All of those are words that go with the sides of a triangle. So this theorem says, well, if the sides are congruent, then the angles are congruent. But it doesn't change the fact that the definition of isosceles triangle has to do with the sides being congruent. Okay? So think about it this way. The isosceles triangle theorem is when you know it's isosceles. In other words, you're starting with sides congruent. You know it's isosceles. Then you conclude angles are congruent by the isosceles triangle theorem. It's the other direction, the converse, where it's not been established that it's isosceles. You just know something about angles. Then you're concluding that sides are congruent. That's converse. From there, you could then conclude that it's an isosceles triangle. But that would be a step that came after, right? So the theorem itself is when you know it's isosceles and you're concluding something about the angles. All right, so like you said, now we can say if 4 is 50 degrees and 4 and 5 are the same, then the measure of angle 5 is also 50 degrees. This is either substitution or transitive. What should I do next? Yeah. Good. 50 plus 50 plus the measure of angle 2 equals 180 degrees. Substitution. Now, you could do this in 2 steps, or you could do it in 1. The 2 steps might be adding the 50 and 50 together, where you get 100, right? So the next step could be 100 plus the measure of angle 2 equals 180. That would be combined like terms. But you really, since you're subtracting it from both sides anyway, you really could just do it in 1 step. Because you're subtracting 50 and 50 from both sides. So that would be subtraction. Does that make sense? Yep. Wait, what do you mean? Which one? So, start with a given again. CE is congruent to CF. So in our diagram, we could mark that again. CE is this whole side. So I'm going to put my congruence right there. And CF is this whole side. Those 2 sides are congruent. Okay, again, based on our given, CE is congruent to CF. And based on the section that we're in, what conclusion can you make? What conclusion can you make here? Okay, what would the reason be? Okay, so since this whole side is congruent to this whole side in the big triangle, the angles across from them are congruent. What is the reason? E congruent to F by what reason? Good, isosceles triangle theorem. Because we start with the sides being congruent and we conclude that the angles are congruent. Okay, look at what we're trying to prove. We're trying to prove that triangle CDG is isosceles. So this is one of those proofs that I feel like when I start with my givens, I make any conclusion I can make, I'm kind of stuck until I really can get a clear vision of where I'm going. Right? So I really have to focus on my proof and maybe work backwards a little bit. So if my final statement is going to be that triangle CDG is isosceles, what do you suppose the statement right before it is going to be? In order to say that that red triangle is isosceles, what do you think the statement right before it would have to be? How could we classify that? Yep, Ella. Good. CD is congruent to CG. If I know that these two are congruent to each other, that would make this an isosceles triangle, right? Now, it could be any two sides, but based on the way this diagram looks, with what's numbered and what our givens are, it's a pretty good guess that it's going to be CD and CG that are going to be congruent to each other. All right, well, what do you think the statement right before that's going to be? Johan? Good. Probably angle 3 congruent to angle 4 would be a conclusion we could make from some other direction, which would then allow us to say that CD is congruent to CG because of the isosceles, the converse of the isosceles triangle theorem, right? All right, so that's pretty logical. So now we can kind of think of what we're given and what we've concluded here in from our givens, and think of this as our goal now. We're trying to get angle 3 congruent to angle 4. So far, we've involved E congruent to F and F congruent to 3. So we need to figure out a way to pull in angle 4. How are we going to get angle 4 to be related to these other angles somehow? Yep. With which triangle? Okay. That actually could work. So she said triangle sum theorem, and that actually could work. I'm going to put that on hold for a minute. Okay. We'll come back to seeing how that works. But that might involve some steps that you guys aren't, well, we're going to go back to that. Yep. So corresponding angles, meaning what with what? Right, F and 4 are corresponding angles, right? So what would be the only way they would be congruent to each other? Is if what? If DG and EF are parallel. So could we get DG and EF parallel? How? Good. Angle E and angle 3 are congruent. And they're corresponding, which makes DG parallel to EF. All right, so let's put that into our proof. First of all, how do we know that E and 3 are congruent? We have to state that. What property would we use here? Which one? Can't use substitution with congruence. Transitive, right? So E is congruent to 3 by transitive property. Therefore, we can say DG is parallel to EF. What would be the reason here? Yes? What would be the reason? Yep, Gabby. Good. Converse of corresponding angles theorem. Well, if DG is parallel to EF, now we can say these other two angles are congruent. By what reason? Corresponding angles theorem, right. So angle 4 is congruent to angle F. Corresponding angles theorem, since we've established that the lines are parallel. All right, so we're trying to say 3 is congruent to 4. Do we have enough congruences to use transitive property and say 3 is congruent to 4? I always have to check my bucket. So in the bucket I go. I've got E and F in the same bucket. F is in there with 3, so I can add 3. E is in there with 3. I have them both in there already. 4 is in there with F, so I could put 4 in here. So yeah, can I say 3 is congruent to 4? Yeah, they're in the same bucket. Transitive property. All right, so if 3 and 4 are congruent, then we can say the sides across from those are congruent. In this triangle here, actually, let me erase a little bit. So now we know 3 is congruent to 4, so we can say the sides across from those are congruent. What's the reason? CD is congruent to CG. By what reason? Yep. Perfect. Yep. Converse of the isosceles triangle theorem. So those two sides are congruent. We can say the triangle's isosceles. By what reason? Definition of isosceles triangle. XY is the angle bisector of angle BYA. Okay, why do they ever tell us that lines are parallel? What do they want us to look for if they're telling us lines are parallel? Anytime they tell you lines are parallel, they want you to find some angle relationships. Remember these 4 angle pairs that we have on the board here: alternate interior angles, alternate exterior angles, corresponding angles, or same side interior angles. They are wanting you to look for those relationships in the diagram if they're telling you that lines are parallel. So right now, let's mark the diagram. BC is parallel to XY. We use these little arrows to show those parallel. And also XY is the angle bisector of angle BYA. If XY is the angle bisector of angle BYA, what two angles would be congruent to each other? Bisector always creates two congruent somethings, right? If it's an angle bisector, it's two congruent angles. If it's a segment bisector, it's two congruent segments. Yeah, Grace. Yep. So in our diagram, we can mark AYX congruent to XYB. What's the reason here? Definition of bisect. Okay. Now, BC is parallel to XY. Like I said, we're looking for some angle relationships. Let me color code these. parallel lines I'm going to make green. We've got one transversal going this way. We've got another transversal going this way. Do you see any of these relationships in this diagram? Kelsey? Okay, alternate interior angles. Which ones are alternate interior angles? Yep. Good. CBY, this one, and XYB, this one. Those are alternate interior angles. You guys see the Z there? Alternate interior angles. Okay, so from our statement, our given that says that lines are parallel, we can make the conclusion that angle CBY is congruent to angle XYB. Now, you want to try to name the angle the same thing consistently through your proof. Yes, this could be called angle BYX, but you don't want to call it BYX over here and XYB over there. You want to try to keep it so that it's the same. So, CBY congruent to XYB. That's this angle and this angle. Here's the Z. All right. What we're trying to prove here is that YB is equal to YC. Again, if you kind of think backwards, think from the bottom up. What do you think the statement right before that is going to be? Again, based on the section that we're in right now, if we're trying to conclude that YB equals YC, what do you think the statement right before it's going to be? These are two sides of a triangle. Yep, Cooper? Yeah, probably this angle here congruent to this angle here. Now, we can't call that angle B because it's more complicated than that, but this angle and this angle, if we could get those to be congruent to each other, then we could say YB is congruent to YC. So actually, the step before the prove is going to have to be a congruence. And the step before that would be these two angles congruent. Now, this angle we've already named as CBY. So we're trying to get angle CBY congruent to angle C. If we can say CBY is congruent to angle C, then we can say that YB is congruent to YC. What would be the reason there? If the angles are congruent, then the sides are congruent. What's the reason? Converse, yep. Converse of the isosceles triangle theorem, exactly. All right, so the problem is we have to get CBY congruent to C. We have these two statements. Is that enough to say CBY is congruent to C? By transitive? No, because we haven't even mentioned angle C yet. How can we pull angle C into this? Yep, Dylan?
If use angle XYA is congruent to C, angle C, with the corresponding angles.
This one and this one are congruent to each other. You guys see that's the corresponding angles theorem? Here's your two parallel lines. We've got this transversal. Both of those purple angles now are formed by green and blue. Green and blue, corresponding angles. Okay, good. So, from this same given that the lines are parallel, you could say angle, this one we called angle AYX, is congruent to angle C. So those are corresponding angles. Sorry, I never wrote the reason here. What was this reason? These two yellow angles are congruent because what kind of angles are they? Alternate interior angles, right. All right, do we have enough now to say CBY is congruent to C? I think we do. I'm going to double check in my bucket. Just for ease of checking, I'm going to call these angles 1, 2, 3, and 4. Here's my bucket. I know angle 1 and angle 2 are in the same bucket because of the bisector given. We said 3 and 2 are alternate interior. And we said 1 and 4 are corresponding. So could I say now that 3 is congruent to 4? Yes, CBY congruent to C. We have enough information here to use transitive property. Now, the proof actually wasn't a congruence, it was an equals. So YB is equal to YC. Why? What's the reason? We proved they were congruent by converse of the isosceles triangle theorem. Now we can say they're equal by what reason? Congruence to equal. Definition of congruence, yep. Yep, yep. It's on your own. Yep. All right, so this next one has some overlapping triangles here. MQ is congruent to PQ. And angle 1 is congruent to angle 2. So let's look at our diagram and mark it up and see what conclusions we can make. MQ, that's this one, is congruent to PQ, that's this one. But notice it's just to here, right? MQ and PQ, congruent. Then we can say angle 1 is congruent to angle 2, because that's given. All right, are there any conclusions you can make from either of those givens? What's a conclusion you can make? Yep, Dylan?
Q is congruent to QL.
Okay, so you're saying because angle 1 is congruent to angle 2, then these two segments are congruent, yes? Okay, I'm going to call it angle QN. I'm sorry, not angle, sorry. Side QN is congruent to side QO. What's the reason? Good. Converse of isosceles triangle theorem, because we're starting with information about angles being congruent and we're concluding the sides across from them are congruent. Okay, what are we trying to prove? Trying to prove that MO, that whole thing, is congruent to PN. That whole thing. What do you think we need to involve here? If we have information about MQ and PQ and QN and QO, and we're trying to prove something about MO and PN, what do you think we need to do here? Yeah, the segment addition postulate. We want to say MQ plus QO equals MO, and PQ plus QN equals PN. Both of these are segment addition postulate. Anybody have any ideas of what we should do next? Yep. Okay, so since we have equations over there with segment addition postulate, we want to get these in the form of equal signs so that we can substitute in for each other. Now, think about the big picture here. We're trying to get this MO equal to PN. Right? That's what we're trying to do. Yep.
Couldn't you just do QN and QO are congruent based on the converse of isosceles?
Yep, that's what we have here. Yep. So now we're ready to substitute. We're trying to get MO equal to PN. So we've had situations like this before. Sometimes they're a little bit tricky, but whenever you have the situation where you're trying to get these two things equal to each other, rewrite one of them. So I'm going to rewrite this one with substitutions involved. So I'm going to kick out the MQ and replace it with a PQ. I'm going to kick out the QO and replace it with a QN. But I'm going to keep MO. I want to keep MO because that is in my proof, right? I'm trying to get that MO to be equal to PN. Well, now I have PQ plus QN there and PQ plus QN there. They're the same exact phrase there, same exact expression. PQ plus QN and PQ plus QN. Well, if PQ plus QN equals MO and PQ plus QN equals PN, that means we can substitute or transitive and say MO equals PN. Substitution or transitive. Now our proof says we want to prove they're actually congruent to each other. So we need one more step saying MO is congruent to PN by definition of congruent. Okay, the rest of the proofs in here I'm going to have you try on your own.